if you would go and have your homework out, and if you would go and hold it up, it should look something like this, but with the gaps filled in. So we had this handout number 7. All right, and waiting on, I gave you an extra one to give to Abby, didn't I? No, I didn't. I thought I gave you an extra one to give to her since she was,
You asked.
that's not the right handout. It looks like this.
Oh, okay. No, that's the wrong one.
Should be in page 57.
It might be tucked into page 57 in your books, because in just a moment I'm going to have you flip the handout over so we can see the back side, and we should have another handout there, but let me check Adam's first. Good. Now flip them all over, and on the back side we should have page 57, number 6. All right. Before we take a look at that, let's quickly review some things we talked about in our last few lessons. One of the big things that keeps coming up, even if the proof doesn't specifically ask for it, is we end up needing to prove triangles congruent to each other. What are some ways to prove triangles are congruent? Abby? Good, and then on Friday we added another one. Abby, you're going to need to copy this down from someone else's notebook, like say Michael's, if you can read his writing. Adam?
SSS.
Side, side, side. We had the side, side, side theorem on Friday in our last lesson. And so again, oftentimes, even if they don't ask for it, we end up needing to get a couple of congruent triangles. Another thing that we had involved an isosceles triangle. And we said that anytime we have equal sides in a triangle, that's a Klang statement. Just as much as perpendicular class means right angles. Just as much as angle bisector means 2 equal angles. Just as much as midpoint means 2 equal segments. So a triangle with 2 equal sides means what, reckon? What's our Klang response if we see a triangle with 2 equal sides in it? Well, it is isosceles. That's not our Klang response. What does that mean if we got a couple equal sides? Dylan? I'm sorry?
They're equal to each other.
Well, that's what I just said. You've got a couple equal sides. They're equal to each other. Yeah, but what does that mean, Noah?
Two equal opposite angles. Equal adjacent angles. Opposite adjacent angles. Equal opposite adjacent angles. Angles opposite equal sides are equal.
Angles opposite equal sides are equal. Not opposite adjacent. Okay, those mean different things. But yeah, angles opposite equal sides are equal. We also had this. If I had an isosceles triangle, in our class notes we proved that if we were to bisect the vertex angle, that line would do a couple of other things. That angle bisector of the vertex angle. From our class notes, what other 2 things were going to be true about that bisector line? Anna? You can almost tell by looking at it, not that we trust our eyes, but we proved that if you bisect the vertex angle of an isosceles triangle, that bisector line will be...
It splits it into 2 equal parts.
It splits what?
The sides.
It splits the sides into 2 equal parts? Or are you talking about this side down here into 2 equal parts? Okay, so it bisects the base. Good, that's one of the things that's true. So if you bisect the vertex angle of an isosceles triangle, we proved you'd also bisect the base. Brandon, do you remember the other thing? Well, yeah, we'll go to the midpoint because it bisects the base. Josh? It's going to be perpendicular to the base. So that's one of the things that we proved. Also in our class notes, we proved this. That if we had an isosceles triangle and you drew the median from the vertex of the vertex angle to the midpoint of the base. So you went from vertex to midpoint of the base of the isosceles triangle. 2 other things would be true about that line. Michael, do you remember one of them? This was actually just from our last lesson. 2 other things true about this line if you draw the line from vertex to midpoint of the base. Dylan?
It bisects the top angle.
It'll bisect the vertex angle. And there was one other thing we proved about this line. Anyone? It'd be perpendicular. I think I heard it from Brandon. It'd be perpendicular to the base. You say, isn't that the same line then? Yep. And if you know that it bisects the vertex angle, bisects base perpendicular to it. If it bisects the base, perpendicular to it, bisects the vertex angle. So kind of a similar idea here. If you're given the one thing, you kind of know the other 2. Also, We talked about lines that we may have to add to a figure. We're going to get some pretty creative ones in our theorem proof today, but lines that you add to a figure to assist in completing the proof. What do we call those, Josh? Auxiliary lines, and we're going to use those in our theorem proof today. For now, let's take a look at the handout and look at the front side there, if you would, please. We were given, oh, that's interesting. Okay, so an isosceles triangle, ABD, and we're also given an isosceles triangle, ABC. All right, so we had two isosceles triangles off the same base, a short one and a tall one. They both were on AB, the base. And then a line was drawn from the vertex of one to the vertex of the other. And we wanted to prove that the two little triangles would be equal to each other. So, let's see here. We've got given isosceles triangle ABC and isosceles triangle ABD with AC equal to BC, AD equal to BD. And we wanted to prove that triangle ACD is congruent to triangle BCD. Already had your statements, reasons here. Obviously, class, every proof, your first statement will just be, and the first reason will always be. So for sake of time, I won't write those in. Well, I'll go and write given, but I'm too lazy to write the other. I will draw an arrow for sake of time. You will not do that on quizzes or tests. Do as I say, not as I do. Don't you love when people say that? All right, number 2, I said Klang angle DAB is equal to angle DBA, and angle CAB is equal to angle CBA. What would be our reason that DAB and DUBA are equal, and that CAB and CUBA are equal? What was our reason there for number 2? Abby? Yeah, in a triangle, angles opposite equal sides are equal. How many had that same reason there for number 2? All right, we've got these two sides equal, so these two angles are equal. And then these two sides are equal, so the smaller angles, and we actually numbered these 2 and 3. So in the proof there, obviously it said that angle 2 equaled angle 3. And then for number 3, I said that angle DAB is equal to angle 1 and angle 2 put together. I said that angle DBA is equal to angle 3 and angle 4 put together. What's our reason there, Michael? Yeah, angle 1 and 2 together are the parts of angle DAB, and angle DBA is made up of 3 and 4. So how many also had the whole is equal to the sum of all its parts, or as I lazily wrote, whole equals sum of parts. Right? Does that make sense? DAB is an entire angle consisted of 2 parts, just add them together. And then for number 4, I said that, well, that angle 1 plus angle 2 can equal angle 3 plus angle 4. Class, I gave you the reason already. It is the substitution axiom. I'll just write substitution. Quantity may be substituted for its equal. Where did that substitution happen, Lana? Which statements did I combine to make that work?
3 or 4.
Yeah, how did I what got substituted where? Because I told you there was a substitution, but where did it happen? Josh?
With number 3, with the angle DAB equals angle 1 plus angle 2.
All right.
And angle DBA equals angle 3 plus angle 4. So they're equal to each other.
Well, but why are these two sums equal, though?
Because they equal the same thing.
They don't. They equal DAB and DBA. Those are 2 different angles.
Yeah.
Right? Adam?
Because
Because obviously I see 3 plus 4, okay, that's right here. I see 1 plus 2, obviously that's right here. But how do I come off saying that these two sums, if you will, are equal to each other?
Because, oh wait, oh, dude, I can't quite remember
Lana?
the word for it.
Oh, it just said in the proof substitution, so I assume it must be. Abby? Number 2, right here. Here's DAB, right? And since DAB is 1 plus 2, then in place of DAB, I just go, there's 1 plus 2. And then here's 3 plus 4, we said that's DBA, so right here, instead of DBA, say 3 plus 4, right there, where it said DBA, right? That's what we mean by substitution. We already had that these two quantities were equal, so I just substitute them in to their places. Then for number 5, I said I wanted you to use the subtraction axiom. Well, what does the subtraction axiom say, Noah? Do you remember? Something about equals, 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 and subtraction. What is the subtraction axiom? Yeah, if equals are subtracted from equals, the remainders are equal. So what equals am I going to subtract from what equals to get what equal remainders? Okay, good. We already said right here that 2 and 3 were equal. So if I subtract 2 from this side and 3 from that side, I'm subtracting equals from these two equal quantities to be left with equals. So what's my statement for 5? Yeah, angle 1 is equal to angle 4. Now, do you have to physically cross them out? No, in fact, I wouldn't. Just using that for illustrative purposes only. So I'll go ahead and erase those ones to confuse you. But yeah, how many had angle 1 equals angle 4 by the subtraction axiom? Because we'd said that 2 and 3 were equal. So then, if we know that this angle 1 equals this angle 4, I know these two sides are equal, these two angles are equal, and these two sides are equal. Well, that's pretty much it. Class, for number 6, I should state that the... Oh, I feel like I missed something. I'm looking at the wrong proof. Sorry. I was like, 7 steps. I'm getting it in 6. Okay, there we go. For number 6, I should state what, Noah?
Triangle AC is congruent to triangle BCD.
And what's my reason, class? Side, angle, side. And how many had that statement, that reason, to close out the proof? Any of you, as you were doing the proof, think to yourself, there's a so much faster way we could have done this. Lana, what was the faster way you thought of we could have done this? Oh, never mind. Okay. She's like, oh yeah, there's a faster way. I don't know what it is. Anyone? Faster way? I could have done it in 3 steps. I'm sorry? CD equals itself by identity, and we got side, 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 side. We could have done it in 3 steps. Now, why didn't I have you do it that way? I wanted you to practice the whole equals the sum of its parts, substitute the parts in for the equal wholes, and subtract away the portions that were already equal to get remainders equal. I wanted you to work that process through because it's a 3-step process you're going to need in the future. This particular proof, we didn't have to have that. So you're like, I could have done side, side, side. Well, yeah, it's true, but I wanted you to work the other. So that's the reason I finagled the proof in such a way you kind of had to do that. Questions on this? Anyone got the proof perfect, though? You got all of the statements, reasons in there. All right, questions on any of them? Questions? All right, flip the paper over. Let's take a look at the back side here. And we were doing page 57, number 6. I'm going to put that up on the board here. And we were given another isosceles triangle, ABC, with equal sides or equal legs, AC and BC. And it says that AB was trisected by segments CD and CE. And we wanted to prove that if you trisect the base of any isosceles triangle, the lines that do the trisecting must be equal. So that was what we were going for, and we actually only need 5 steps, apparently, for this proof. All right, so on your paper, should have drawn what appeared to be an isosceles triangle, and then the fun part was kind of locating the trisection points to the best of your ability. Y'all remember when we tried to locate trisection points earlier? When we first learned about it, we did, just practicing with it. A little harder to do than midpoint guesstimations, but this is what we have. A, B, C. We have equal segments here, and then these points here. So obviously statement number 1 was already given to you. Isosceles triangle ABC with AC equal to BC, CD and CE trisect AB. Number 2, they wanted you to state something to be true because angles opposite equal sides in a triangle are equal. What should we state in number 2, Lana? What angles must be equal because they're across from equal sides? Good. We have to tune out the noise of these 2 lines and look at the triangle as a whole and say, well, in this whole triangle, across from BC is angle A, and across from AC is angle B. So I can say that angle A equals angle B. How many had that as your statement number 2?
I have it.
All right, questions on that? All right, number 3, it said that AD equals BE, and by the way, they could have said equals DE if they wanted to. What would be our reason that AD, BE, and if we wanted to, DE, are all equal to each other? How do we know they're all equal? Lana?
Well, I just put a subtraction thing, but
No. Dylan? Definition of trisection, right? Trisect means to divide into 3 equal portions, right? Bisect divided into 2 equal parts. Trisect divided into 3 equal parts. Now what made it hard is they didn't write this. So you don't see 3 equal parts listed out. They only specifically mention these 2, but they are equal even if they don't mention the other piece that is also equal. Does that make sense? So definition of a trisect or definition of trisection, something along those lines. How many had something about a trisector, definition of a trisection, definition of trisection points, I suppose, could have worked as well. And then boom, they're already ready in number 4 to say they've got some congruent triangles. ADC congruent to BEC. And what would be our reason here on number 4, Brandon? Yeah, I've got these 2 sides equal, these 2 angles equal, these 2 sides equal. How many had SAS? Capital letters, of course, for number 4. All right. And then number 5, they wanted us to get the proof, remember, was to prove that the lines that do the trisection are in fact equal to each other. What was our reason here on number 5? Adam?
CPCD.
Yeah, we've got congruent triangles, and those are corresponding parts, right? CD, CE, they're corresponding parts of those congruent triangles. So they're equal. How many were perfect on proof number 6 on page 57?
stopped for the reasons for 4 and 5.
Okay, remember, if you have congruent triangles, that's either SAS, SSS, ASA, LLLA, if you happen to be going with right triangles. And then after the triangles are congruent, angles or lines can be equal by CPCTE. Question, Brackett?
On number 2, I said angle CAB equals angle CBA.
Okay, perfect. Yes, CAB and CBA are the same thing, so it's not a problem if you say cab equals cabab. Is that what you had then?
Yes, sir.
So were you perfect on the proof? Okay, great job. Good. Any other questions, comments? Questions, comments? Yeah, it's not wrong to use the 3 lettering. I'm just lazy and generally wouldn't, but unless I had to, right? If I had to CDA, for instance, well, I either got a number or use 3 letters there. Though I'd say 1, 2, 3, 4, 5, 6, 7, just to get out of saying any 3-letter names because I'm that lazy. All right, good. Any other questions, comments on this? All right, Theorem 5 in your notebooks. Go to the Theorems Corollaries section. Theorem 5 in your notebooks. Take a little bit of a break from congruent triangles here in Theorem 5. So theorems, corollaries page. Now notice there was not a corollary 4 dash anything. Theorem 4 did not have a corollary. That's fine, it doesn't have to have one. Theorem 5, right below Theorem 4 in your notebook, says this. An exterior angle of a triangle, an exterior angle of a triangle, an exterior angle of a triangle is greater than either opposite interior angle. An exterior angle of a triangle is greater than either opposite interior angle. An exterior angle of a triangle is greater than either opposite interior angle. Don't we love shorthand? Once you have that down, if you would, turn to the proofs of theorems corollary section. And this is not a corollary, so we're not going to put it on the back of Theorem 4. You say, that's wasting space. I don't care. We'll grow another tree, all right? They plant new trees every day, okay? And when your children are old and they need paper for their geometry notebooks, they can use that tree. We're going to use the trees we have now. All right, new sheet of paper in the theorems or proofs of theorems corollary section. At the top of a new sheet of paper, go and write this out. Theorem 5. An exterior angle of a triangle is greater than either opposite interior angle. Exterior angle of a triangle greater than either opposite interior angle. Once you have that down, go and draw a triangle. We'll call it ABC. So once you've got this written at the top of a new sheet of paper, right below it, go ahead and draw a triangle. Call it triangle ABC. And we want to prove that in any triangle, I just chose one at random, ABC, we want to prove that an exterior angle. What's an exterior angle, Michael?
Extend one.
Yeah, we're going to have to extend the line. So let's take AB and let's just extend it out to a random point. Let's just call that X. It doesn't really matter how far we extend it. It just has to be extended at least a little bit in order to get some point out there to get an exterior angle. So we see now the exterior angle is CBX, correct? All right, so we want to prove that the exterior angle here, CBX, is greater than either opposite interior angle. Well, begs the question, which angles in the picture are opposite interior angles, Brecken?
A and B.
Is B opposite interior? It's right here next to the angle that's exterior. It's actually an adjacent interior.
A and C.
A and C. How many think in A and C? All right, so here's what we're given, first of all. We're given triangle ABC with AB extended to any point X. That just means you don't have to extend it a particular special length or anything. We don't know, by the way, that AB and BX are equal. They kind of look equal, don't they, on my picture? We don't know that they're equal or anything weird like that. It's just a random point where I chose to extend the line. We want to prove that if you have an exterior angle formed by extending a line, that the exterior angle CBX is greater than either angle A or angle C. I want to prove that it's greater than either opposite interior angle. Stay. Once you have that down, 2 columns, statements, reasons. Copy down your first statement and your first reason. All right, so let's think about this, because I have no plane, correct? There's no equal sides to my triangle necessarily, so there's no plane there. No perpendiculars, no midpoints, no angle bisectors. I really have no plane, so we're ready for analysis. I'm going to prove something is bigger than something else. Well, that actually narrows it down, doesn't it? Because nearly everything we've talked about to this point has been this is equal to this, or this equals, right? There haven't been a lot of times where we said that something's bigger than something else. When have we talked about something being bigger than something else? No? I'm thinking of two axioms, one informal statement. I think that's it. I can't think of any other times where we said that something's bigger than something else. I got two axioms and an informal statement. Brandon, what are you thinking of? Well, he looks up some other things.
The whole is greater than any part of it.
Yeah, that's one of the things I was thinking of. The whole is greater than any of its parts, all right? Noah, have you found another statement where something's bigger than something else?
If the first of three quantities is greater than the second quantity, and the second is greater than the third, and the first is greater than
Okay, the first is greater than the second, second's greater than the third, and the first is greater than the third. Those are the two axioms I was thinking of. There's one informal statement about something being bigger than something else. Anyone remember what that one was? Good, we're looking it up if we don't know. That's exactly what you should be doing. All right, Noah found it?
the sum of two sides of the triangle is greater than the third side.
Good, sum of two sides of a triangle is greater than the third side. Now, of those three, only one of them deals specifically with lines, correct? The other two axioms could deal with anything, but the informal statement Noah just read dealt specifically with lines. I'm trying to prove something with angles. So does it make sense that that informal statement is kind of off the table? So we're down to proving if the first is greater than the second, second is greater than the third, and the first is greater than the third, or whole is greater than any of its parts. One of those two statements has somehow got to work for me. As we look at it, we're like, well, if CBX is bigger than something, and that something is bigger than A and C, then it's bigger than A and C, right? But what would the something be? I mean, angle B, perhaps? I mean, that would make sense, right? If this is greater than angle B, and angle B is bigger than either of these two, then this is bigger, correct? Can I prove that an exterior angle is always bigger than the adjacent interior? Sounds like something we had on a test not long ago, right? Is an exterior always bigger than the adjacent interior? Nope. Well, there goes that. Plus, is there any way to know that B is bigger than the other two guys? Not necessarily. Okay, so yeah, so the only thing left is somehow we've got to say that the whole is greater than any of its parts. But that would be saying that this is whole and one of these is a part. Only problem is, are either of these a part of that angle? No, but what if I made an angle that was equal to one of these, and I made it here so that it was a part? That makes sense? For instance, Noah is bigger than his arm, right? Because the whole is greater than any of its parts. But what if we'll just take a crazy illustration. Let's suppose Noah's arm is exactly the same size as Brecken's arm. Okay, not that we're actually going to do a real physical substitution, but mentally, right, we could say, okay, we can substitute then. If Noah's bigger than his arm, and his arm is the same size as Brecken's arm, then Noah is bigger than Brecken's arm. Does that make sense? Right? Strange analogy, I know. That's kind of what we're going to have to come up with here. We're going to have to come up with an angle that is part of the angle, and then say it's bigger than that, but that angle's going to equal one of these. I'm going to lock in, and you're going to see why in a few minutes, on angle C. I want to get an angle that has to be exactly the same size as C, and I put it here. The problem is I don't know the measure of C, so I can't go off of its measure. We're going to use some pretty creative auxiliary lines. Step number 2. And again, no, I wouldn't expect you to come up with this on your own, don't worry. Step number 2, I want you to put this. Locate M, the midpoint of BC. Locate M, the midpoint of BC. Now, if I already had a midpoint marked, could I locate a second midpoint, class? No, because only one point can divide a line into two equal segments, correct? But because we have not specified that there is a midpoint yet, if I locate the midpoint and we call it M, that's now the midpoint of BC. Because there is one, we hadn't located it yet, I just now located it. My reason is only one point can divide a line into two equal segments. Only one point can divide a line into two equal segments. I am saying that M is that midpoint. You say, it doesn't quite look like the midpoint. Your eyes are wrong. We don't trust our eyes. That's the midpoint. Any other point you say is the midpoint is wrong because that is the midpoint. Now again, could we do it perfectly? Sure. I'm just lazy. We're going to just say it's the midpoint. Then step number 3, we're going to draw an auxiliary line AM. So for number 3, say draw AM. Now, I'm not going to have you do this because we're recording and I can't have minors on video. Yeah, you're still a minor too, aren't you? Yeah, I can't have minors on video. Okay, so without parental consent, and I haven't bothered to get parental consent from any of your parents. All right, so too much legal trouble. We'll just keep you off the video. So anyway, if I were to call you up to draw AM, you shouldn't come up here and be like, but where do I put it? We should all know where AM goes, right? From A to M. Do it on your paper. And why did you know exactly where AM should go? Because through 2 points, only one straight line may be drawn. Or the faster way to write it is this: 2 points determine a straight line. Now, what did I just do? I took what was one triangle and I turned it into 2 triangles. Are those 2 triangles going to be congruent? Probably not. I do know I'll have a couple equal segments here, and this line equals itself, but do I have any way of knowing those 2 lines are equal? So they're probably not 2 congruent triangles right there, but just thought I'd point that out. We have 2 triangles now. Now, this line AM can be extended indefinitely or limited at any point, correct? If I were to extend it, but then measure this with a compass, I could mark off exactly this same length onto the extension, correct? That's what we're going to do next. Number 4, extend AM its own length to a point D. Extend AM its own length to a point D so that AM equals DM. So we are extending the line, but we're extending it exactly the same length that AM is, so that AM equals DM. Make sense? And the reason here a line may be extended indefinitely, indefinitely, or may be limited at any point. Okay, finally something I can use shorthand on. All right, a line may be extended indefinitely or limited at any point. Now, if I were to tell you to draw BD, all of you know exactly where that line should go, correct? Why? What would be my reason if I said number 5, draw BD?
Only one line can be drawn between 2 points.
Only one line may be drawn between 2 points. Or once again, 2 points determine a straight line. So we draw BD. Like I say, pretty extravagant auxiliary lines going on here, right? And again, this is why I would not ask you to try to do a proof like this. But do you follow what we're doing? Not why I'm doing it yet, but you understand what I'm doing and the stated reasons that justify them. Again, the reason doesn't tell why I did it. It justifies the fact that I can. Now look what I've got now. 3 triangles. ACM, BAM, and DMB. Dum. Just put a U right here, and just kidding. All right. All right. Anyway, put U right there. It's like, who's he talking to? Put U right there. People point at Noah. What is this? Come on now. It's hatred for this. Love your brethren, right? Brother in Christ.
That's all right.
All right. All right. So we got 3 triangles here. Now, I want you to note, first of all, we did locate M as a midpoint, right? We built in a claim that we never claimed off of. What is the claim to M being the midpoint of BC class? So, CM equals BM, right? Let's go ahead and get that down because we kind of missed it earlier. CM equals BM. And the reason those 2 segments are equal, Lana?
Because it's gonna say M's the midpoint.
Well, that is exactly right, because M is the midpoint, and a midpoint is a point that divides a line into 2 equal segments, right? That's the
Definition
of a midpoint, right? So definition of midpoint. I said this before, and I'll say it here. A lot of times, if you find yourself saying, well, why do we have right angles? Well, because I have a perpendicular. Why are those 2 segments equal? Because there's a midpoint. Why are those 2 angles equal? Because I have an angle bisector. If you find yourself saying, because I have this, it's probably definition of this. Okay? Not always, but oftentimes. For instance, I want you to call this angle 1 right here, angle AMC. And right here, angle DMB, I want you to call it angle 2. Thoughts on angles 1 and 2? Dylan?
They're equal.
Why?
Because they're vertical.
Because I have vertical angles. Now, this is one time where it's not definition of vertical angles, okay? Remember, the definition of vertical angle says the non-adjacent angles formed when 2 straight lines intersect, okay? Definition of vertical angle says nothing about equality. But we did have an informal statement, Brandon, that said,
All vertical angles are equal.
yeah, vertical angles are equal. So we can say angle 1 equals angle 2. This is one of those that you're going to be tempted to say definition of it. It's not. It's just that vertical angles, angles plural, are equal. Now look closely at the 2 triangles AMC and DMB. Thoughts? Adam? This triangle here and this triangle here. Thoughts?
They're congruent
Why?
because they have side angle side.
Side angle side. How many thinking the same thing Adam said? Yeah, we got congruent triangles here. Number 8, let's state that AMC is congruent to, let's see, D corresponds to the A, M corresponds to the M, of course, and then B corresponds to the C because of side angle side. I'm going to call these 2 angles 3 and 4. Notice that this angle here, 3, corresponds to the angle at C, right? So since they're corresponding angles in 2 triangles that are congruent, what could we state next, Michael?
Angle 3 equals angle C.
Angle 3 equals angle C by
C equals CTE.
Is that the last thing?
what?
Is that the last thing?
No, it's not. I'm running out of board space here, but we're going to squeeze it in here. Now go back to this. Brecken's arm is angle C. Noah's arm is angle 3. Brecken's arm is the same thing, the same size as Noah's arm. Correct?
Yeah.
Noah is this. Noah is bigger than his own arm, isn't he? Number 10, All right, small. Number 10, angle CBX is greater than angle 3. How do we know CBX is bigger than 3, class? The whole is greater than any of its parts. But since 3 and C are equal per statement 9, class, what can we do? Substitute. Good, Abby. We can plug a C in place of the 3. Just take that since it equals 3 and put it right there. And number 11, angle CBX is greater than angle C by substitution. And that takes care of the first half of the proof.
First half.
Well, yeah, there's still angle A. All right. In all fairness, we're not going to do the other half, but I want to talk through it because to be logically accurate, what about angle A? We would do the exact same steps, except we would have located this midpoint. We would have drawn that line. We would have extended that line its own length, and we would have connected to right here to show that angle A is equal to this angle here. We could have also extended this line through here to show that this angle is the same size as CBX because they're vertical to each other. And since this angle is bigger than this angle, then this angle is also bigger than that angle because these two are equal. But since this angle is bigger than that one, which is equal to this one by CPCTE, then this one's bigger than A. And that's how we would have proven it. It would have been all the exact same steps again. We would have just had to do a second set of stuff right alongside it. So we still would have taken 11 steps. We would have just had draw AM or locate this midpoint and locate that midpoint. Draw this line and draw that line. Extend this line its own length and extend that line its own length. So we would have basically doubled up everything we did on 2 through 11 for sake of time. Well, maybe another step or two for the substitution down here with this extra exterior angle that's equal. But pretty much it's the same proof all over again. For sake of time, I'll let my verbal explanation suffice. Not asking could you come up with this on your own, but do you follow what we did? Does that make sense? Question, Michael?
No.
Agreeing that you got it? All right, questions on this. So what do we walk over? Yes, sir.
So it says or. So you get to choose which one, or do you got to do both?
Well, technically to say and implies an addition of the two. So we used or, not to say one or the other, but the fact that either of them, it's greater than either one of them, whichever one you happen to be paying attention to. It's just to avoid ambiguity with the word and. We're like, does that mean together or does it mean separately, right? For instance, if I say I'm taller than Brandon and Dylan, does that mean the two of them stacked on top, or is he just taller than both guys, like individually, right? I'm taller than Brandon or Dylan. Okay, he's taller than either one. That's the only reason for that wording. Great question, by the way. Good, any other questions on this? All right, so from this point forward, any exterior angle, and by the way, the classic example here would be, what if the exterior angle is really small? It's still going to be bigger than either this one or this one. Because even if it were a small angle like this, you could still locate a midpoint. You could still draw a line. You could still extend its own length. You could still draw a line back so that this angle would still equal that one. And the whole is still greater than any of its parts. So yeah, this proof works regardless of the shape of the triangle. It's a little easier to see when you have more space. But questions? Terms definition section of your notebook. You're going to read about this tonight in your homework reading, and it's a really fun way of doing proof. We're going to look at tomorrow in our next lesson, something called an indirect proof. So terms definition section, I want you to go and get down that term, indirect proof. And this is one of my favorites. My high school geometry teacher loved these. My college geometry teacher felt that these were even better proofs than direct proof, and I may differ somewhat with him on that, with apologies to Dr. Lane. But anyway, indirect proof. Okay, here's your definition. An indirect proof is a proof that begins by assuming the opposite. An indirect proof is a proof that begins by assuming the opposite of what is to be proven. An indirect proof is a proof that begins by assuming the opposite of what is to be proven. And then, a proof that begins by assuming the opposite of what is to be proven, and then proves that assumption impossible. And then proves that assumption impossible. Or as my college teacher liked to say, ridiculous. Which is just a great word to use in a class like geometry where everything's so logical. A proof that begins by assuming the opposite of what is to be proven, and then proves that assumption ridiculous. For instance, if we wanted to prove that Noah was smart, I don't know, you're way back there, I'm still picking on you. I don't know what the problem is here. I missed out last year, that's what it was. All right, so if I wanted to prove that Noah is smart, first of all, we could assume that Noah is dumb as a box of rocks. Well, we've got some evidence that would tell us he's not dumb as a box of rocks. So it's impossible that he's dumb as a box of rocks. Well, that's not quite the opposite, right? Because there's still a third choice, right? He may not be smart, he may not be dumb, he could be average, right? Okay, well then let's assume Noah's average. Well, we could look at some things to prove that's impossible too. So if it's impossible that he's average, and it's impossible that he's dumb, the only thing left is that he must be smart. If you will, in parentheses at the end of that definition, in parentheses at the end of the definition, write down two things. There's two other names for an indirect proof. One is called an informal proof. It's also called an informal proof. The idea being we don't necessarily lay out statements and reasons in a formal layout. A little less writing to do, okay? So it's also called informal proof. The other name is a little more practical name. It's sometimes called proof by contradiction. Proof by contradiction. So sometimes called an informal proof or proof by contradiction. Because the crux of the proof is to arrive at a contradictory statement. And we're going to do a couple of proofs tomorrow that are indirect proofs. And we'll talk more about it tomorrow. You'll read about it tonight. So for homework this evening, need you to read pages 61 and 62. So not a lot of reading, but you'll want to make sure you take the time to do the reading. Read pages 61 and 62. While you're reading in your books anyway, go and study over pages 55 to 59. Go and study over pages 55 to 59. Noah has a very suspicious look on his face back there. And then in addition to that reading and studying, let's continue practicing proofs by doing handout 8. All right, so Gavin, and if anyone else is watching on YouTube, doing handout 8. For you guys in the class, you just put handout because I'm giving you the handout. Now the hard part is don't get this confused with other handouts, right? It's a handout that has empty spaces on it, okay? So a 7-step proof to do for homework this evening.
The first step is still.
There we go. See, I'm trying to help you out here, right? All right. Well, when the bell rings, you are dismissed. There it is. You're dismissed. Have a great day.